Hello, my name is Rita Horner. I'm the Technical Marketing Manager in the Mixed Signal IP Group.
And I'm David Rennie, and I'm a Senior Analog Design Engineer in the Mixed Signal IP Group.
An eye diagram is a great tool to be able to assess the quality of a signal very quickly. But some eyes are very fuzzy. And let's take a look at this fuzzy eye that I have here. What causes this fuzziness about the eye diagram?
That's a really good question, Rita, and it's an important question in the field of signal integrity. When we see this fuzziness, the cause of it is a type of distortion known as intersymbol interference. So what is intersymbol interference? Well, let's start by looking at this channel response we see here. Now, this channel response is just an example, but it shares something in common with basically any channel in a wireline data communication system in that we see a frequency-dependent attenuation. So high-frequency signals experience a higher amount of attenuation compared to low-frequency signals. Now, why is this important? Well, in a binary data communication signals, we are sending a series of ones and zeros. And these series of ones and zeros, depending on what the pattern is, will have a different type of frequency content. So here we see an example of 4 different data patterns. Number 1 is a repeating 1010 pattern, and this actually has the highest amount of frequency content that you can get in a data pattern. 2 and 3 again have repeating patterns, but with lower and lower frequency content. And finally, 4 is a pattern that has both low frequency with high frequency pulses in the middle of them with the low frequency pattern. So if we take these signals, these data patterns, and we put them through the channel we showed previously, we can look at the response using eye diagrams. And that's what we see here. The red filled in areas of the eye diagram represent the eye openings. And obviously different data patterns, as we can see here, different data patterns give us different eye openings. So why is this important? Well, for a robust system, we want as large an eye opening as possible. But one of the things we see is that as the data pattern becomes more realistic, more closer to a random pattern, for example, if we think back to 4, which was a mixture of low frequency and high frequency data, which is what we would expect, our eye opening gets smaller and smaller. In these patterns, we have a very finite number of trajectories, a finite number of patterns, and we can see that we have these well-defined blue lines. But in a real random data pattern, we don't have these very particular data patterns. We have all kinds of data patterns. And what that means is that instead of these well-defined trajectories, we get all the different types of trajectories in the middle of these, and that is really what we get how we get these fuzzy eyes. The fuzziness is fundamentally due to the random data patterns containing random frequency content, and these frequency content experiences a frequency-dependent loss, and that's how we get this fuzziness.
Can we do something about it? Can we minimize the fuzz or even get rid of it?
That's a really good question, and that's fundamentally what we try and do with equalizers. So an equalizer is a circuit which attempts to flatten out the frequency response of the channel. So instead of having this frequency-dependent loss, we ideally want a flat channel response. Now, this figure here, we see in blue the original frequency response of the channel. The red dashed line shows the frequency response of an equalizer. And finally, the black line shows the overall system response, including both the channel and an equalizer. Now, it's not perfect. The black line is not perfectly flat, but it does have less loss than the original channel, and that's what's important here. This was designed for an 8 gigabit per second data rate, and as such, the frequency of interest is 4 gigahertz. That's the highest frequency signal that we can have. And the original channel had more than 12 dB of loss, but after the equalizer, this is improved by more than 6 dB. So it's not perfect, but if we look at the resulting eye, we can see that it looks much better. The eye opening is, whereas before it was almost closed, now we have a nice wide open eye. If we had perfectly equalized, we wouldn't see any fuzz at all. And we still see a fair bit of fuzz, but the key thing is that we have an open eye, and this will give us a robust system.
So is this fuzz due to the higher data rates, or does it have anything to do with the quality of or the type of equalization that is used?
So any system that sees a frequency-dependent attenuation will see intersymbol interference. However, it's only as we've gotten into the multi-gigabit per second data rates that this effect has become significant enough that we need these complex equalizers in order to deal with the intersymbol interference.
Thank you, David. That was great. For more information, please visit us at Synopsys blogs. The eyes have it. Thank you.